Today we are fortunate to get Professor Ashitava Ghosal, a senior professor in IISc, to have our next session. I have his brief CV. I will just read out. Ashitava Ghosal is a professor in Mechanical Engineering Department and the Center of Product Design and Manufacturing at IISc Bangalore. He completed his PhD from Stanford University, California in 1986. MS from University of Florida in 1982 and BTech from Indian Institute of Technology, Kanpur in 1980. His broad research areas are kinematics, dynamics, control and design of robots, and other computer-controlled mechanical systems. His current interests are in design of biomedical devices and tools for minimally invasive surgery, design of parallel mechanisms of tracking the sun for concentrated solar power systems, and product design. He has authored a textbook entitled Robotics, Fundamental Concepts and Analysis by Oxford University Press. He has 3 patents, around 60 archival journal papers and 70 papers in national and international conferences. He has guided 9 PhDs, 15 MSc Engineering and more than 35 ME students. He is currently serving as the Vice President of Association of Machines and Mechanisms in India, and he is a member of Executive Council of International Federation for Promotion of Mechanisms and Machine Science, and in the Technical Committee for Robotics and Mechatronics. With this, sir, I invite you for delivering your lecture. Thank you.
Thank you, Professor Sudeep and Professor Joy, for inviting me here. So this session is on dynamics of serial manipulators, because I am told that there will be other sessions on parallel robots and also on control and sensors and actuators. So this is a little bit like a classroom lecture, because there will be a lot of math and a lot of equations and so on, but we'll see that some of these things are required. I mean, if you ever want to do any robotics, you have to learn math. There's nothing you can do about it. So this is a shortened version of a set of lectures which are available in NPTEL. How many of you know what is NPTEL? Okay. So about 3 or 4 years back, I wrote a set of large number of lectures on NPTEL on various aspects of robotics, and this is taken from there. So if anybody is interested in more details, more advanced concepts, more simulations, results, videos and so on, you can go to the NPTEL website and see this. Or you can also look at my own web page, and there is a link to that NPTEL material. Okay. So this is in roughly in 3 parts, and as you can see, the parts are in some sense organized as how to derive equations of motion. So I am going to discuss only one way of deriving equations of motion, which is called as the Lagrangian formulation. There are other ways. Then I'll show you some examples, and again, this is being a little bit like an academic type of lecture. It will be a very simple robot, but you should not get into leave this talk saying that only it can work for only such simple robots. It can be used for anything. And then I'll show you some simulations. So basically, why do we derive equations of motion? We need to do some simulation. We need to do various things which are useful later on for design and also for seeing what the robot is doing. Okay. So just a little quick introduction. This is a repetition maybe of what Professor Isaac Kurian had also discussed. So in robotics, or like in any other machine design or mechanism design, mechanism analysis and design problems, we first look at kinematics, which is basically we look at how the bodies are moving. Okay, we do not really recognize or consider what is the cause of the motion. The next important thing is dynamics, in which basically we want to find out the links of the robot. So robot is made up of rigid bodies connected by joints, and we want to find out how the motion of these links are moving when some external force or moment is applied. Okay, so the main assumption in this set of talks is that the links are rigid. It need not be rigid, it can be flexible. Then of course the equations of motion are much more complicated. Okay, so once you make an assumption that these are rigid, you will derive what are called ordinary differential equations. Whereas if you look at flexible, something else will happen. Okay, and these are also called equations of motion. And there are various ways of deriving equations of motion. Okay, there is Newton-Euler method, there is Lagrangian, there is Kane. So in Newton-Euler, basically we look at what we do in high school physics. So we draw free body diagrams, we find the linear and angular velocity, we find forces, we then do F equals ma and whatever the equations of motion we apply. Okay, so these are called Newton's laws or Euler equations. Whereas in Lagrangian formulation, this is an energy-based method. So we derive the total kinetic energy, maybe the potential energy, various other forms of energy. If you want to include friction and so on, you can do it. And the result is, the basic idea is that we get a scalar quantity, a single scalar. Okay, and then with that scalar, we do a set of, it's like a recipe. We have to take certain derivatives in some particular way and then assemble. Okay, and hence some people find it much easier. Whereas if you want to do this Newton-Euler, you have to find out direction of forces, vectors, velocities, various things you need to consider. There is also a Keynes formulation, which I don't want to get into. Okay, so each formulation has its own advantages and disadvantages. So if you were to do Newton-Euler, then you have much better idea about the directions of velocity, forces, and so on. Okay, you can also include friction. You can also include various other things which are not so easy in the other two formulations. It can be done, but it is easier in Newton-Euler method. Okay. So I am going to do only Lagrangian formulation today. If anybody is interested, we can see. There are lots of textbooks. It is also in the NPTEL website. Various places are there. So there are two main problems in robot dynamics. One is called as the direct problem, which is basically we want to obtain the motion of the links given external forces and moments. And the other one is the inverse problem, okay, which is exactly the opposite. If I give you the motion, if I tell you that the robot is moving with so much velocity, so much speed and rotating and so on, how do I find what is the joint torques and forces? Okay. The direct problem involves solution of ordinary differential equations. So you have to numerically integrate certain equations of motion, because most of the time you can't solve them analytically. You have to go to use a computer. And this is called simulation. Okay, the word used is, if you want to do the simulation, or if you want to solve the simulation problem, you have to solve the direct problem. Inverse dynamics, on the other hand, is basically used as a design tool. So if I know that my robot is going to do such and such task, it has to go pick up, put something in between, it has to attain so much velocity, so much acceleration and so on, then I solve the inverse problem to find out how big the motor should be, how much torque is required from the motors. Okay, so it is a very useful problem. It is also used for model-based control, which we will do tomorrow morning. So you can use the inverse problem to do control. The key interest in all these dynamics problems is computational efficiency. Okay, we can get equations, you can get so many equations. So the important, one of the challenge which is now more or less solved, is to find out how efficiently you can simulate these equations of motion, how efficiently you can solve the inverse problem. Okay, so in computer science language, they have this complexity. Okay, so if you have n links, so if you have a 6 degree of freedom robot with 6 links, or if you have a much larger robot with many other links, okay, what is the computational efficiency? So what we are looking for is linear complexity. So this is what it means, that I want the number of computation to increase linearly with the number of links. Okay, so if I have 6 links, I do so many multiplication. If I have 7, I do so many extra. Okay, how does it scale? Linear. That is what we are looking for. You can also do log n, in which case you have to use parallel computing. So that we will not discuss here. Okay. This I will not discuss, but just to tell you that everything is not always linear. Okay, so if you have a parallel robot, which I'm sure it will be discussed tomorrow or day after tomorrow, you don't have so easily linear complexity. Okay, you also don't have only ordinary differential equations. So you get what are called as differential algebraic equations, which are much more difficult to solve. Okay, so in that context. So what do we need to form these equations of motion? One of the most important thing is to represent mass and inertia of each of these links. Okay, mass and inertia of the rigid bodies which make up the robot. And what is mass? We all know. So if you just, this is some strange shaped link. So how do we find out mass? We know the density, we know the volume, and we can find out the mass of the rigid body. Similarly, how do I find out inertia? For inertia, there is also a little bit more complication. Inertia is always with respect to a coordinate system. So you have to say with respect to this particular reference coordinate system, I have this Ixx, Iyy, these are all well known, so I'm just repeating it very quickly. Okay, and there are formulas for Ixx, Iyy, which is well known. So for example, Ixx is this, integral of y square plus x square dv and so on. Okay. The important thing to note is this inertia is a tensor. Okay, as I said, you need a different coordinate system. If you find the inertia in one coordinate system, let's say with respect to the CG of the object, it will be different if it is with respect to another coordinate system. Okay, but for every time, it is always a positive, definite, and a symmetric matrix. Okay, so there are reasons. If it were not so, what would happen? You will have lots of problems. Okay, if it is a symmetric, then you can show that you will have what are called as principal moments of inertia, which are also positive. Okay, so I can have Ixx star, Iyy star, and something which are these principal moments of inertia. So if you look at the back of some old mechanics book, they will say a rod has half ml squared, okay, or 1 by 12 or 1 by 3 ml squared or something like that. So those numbers are basically the principal moments of inertia about maybe the center of the rod or about some, so we can find out that those are always positive quantities. Okay, and how do we find the inertia of actual robot part? So basically what you do is you see what this robot part is made up of. So maybe it's a tube with some holes, or it's a box with some holes with some motor attached. So we can find out the inertia of this entire robot, entire link with whatever else is there by using some tricks. So one of them is this: you can transform the inertia from one coordinate system to another coordinate system by some formula, which is also well known. You can also use what are called as parallel axis theorems. Okay, so if you know what this inertia about this axis, about some other axis, we can find out. And then also, so suppose there is a hole, you have made a hole to take some wire. So how do you find the inertia of this rod with a hole in it? So you can find out the inertia of that, assume there is a mass there, and subtract it. Okay, so using this addition and subtraction and transformation of coordinates, you can find actually the inertia of a single rigid body, a complicated part. So those of you who have done any course in CAD, so if you can draw any odd shape, there you can make holes, you can attach a screw, you can do whatever you want, and then when you click on the object, it will tell you all the inertia components. Okay, all that it is doing is, it is doing addition, subtraction, rotation, and transformation between different axes. Okay, so you can find out the inertia of not simple rods and boxes, but any complicated shape. So that problem can be solved. Okay, so once you have the mass and inertia, then we can look at how to derive the equation of motion. Okay, and as I said, I'm going to use the Lagrangian formulation, and this is how it goes. So it's an energy-based formulation involving kinetic and potential energy. So what is the kinetic energy for any link, any single link of the robot? It is nothing but half mv square plus half I omega square. Okay, it is written in this strange form, but otherwise it is just a basic idea of what we do from POC or even high school. Okay, so we can find what is the mass of that link, we can find what is the linear velocity of that CG of that link, you can find the inertia matrix of that link, you can find the angular velocity of the link, and you just compute this. Okay. There are some tricks. If you, Professor Kurian must have told you about how to find the linear and angular velocity of the origin of the coordinate system. So when you go from one link to another link, you can find out the linear and angular velocity. So there are formulas in where you can do what are called as propagation. So if you know what is the first link, I can find out the second link, from second link I can find out the third link, and so on. Okay, so there are these propagation formulas for linear and angular velocity, but they are for the origin. But if you want, you can convert it to some other coordinate system, because this is just a normal vector, like any other vector. I can convert from the origin or the I coordinate system to the 0 coordinate system, and so on. So these are all well-known tricks how to convert vectors from one coordinate system to another coordinate system. So it's a good idea to convert everything to the 0 coordinate system, which is the fixed coordinate system, your reference coordinate system. Not necessarily, you can show that these two are equal. This is some other I coordinate system, it is also the same as this. And there is an obvious reason, because the kinetic energy is a scalar, it's just a number. Okay, so the numbers don't depend on coordinate system. Okay, only vectors and matrices or tensors depend on coordinate system. So I find the coordinate system, and this is a very well-known propagation formula which we use very often. So if I know what is the angular velocity of the I minus 1th link, okay, and then I see that the I minus 1 link and the ith link are connected by a rotary joint, which is theta dot. There is a rotary degree of freedom in between both of them. So from I minus 1 to I can use this formula. Okay, if it is the two links are joined by a sliding joint, which means that there is no relative rotation between the two links, then the angular velocities are same. Okay, here the angular velocities is the previous angular velocity plus the rotation at the joint. That is the basic idea. Okay, and all these things are to make sure that the coordinate systems and the vectors are added properly. Linear velocity also I can find out if I know the linear velocity of the origin of the link. Okay, then v plus omega cross r. This is the standard equation which everybody we use, but this is written in a form so that it can be automated, it can be used in a program. Okay, I can program these things, I can draw these links, and then can automatically calculate all these linear and angular velocities. Okay, so that is what is mentioned here. So if I know what is that happening at the 0, which is the fixed base in a serial manipulator, then I can just keep on using these equations in an iterative manner and find out all the linear and angular velocities of all the links. Okay. So dynamics is a very old problem. People have worked on it in the 80s, 90s, lots of things. So many of these things are now very fine-tuned. They know exactly what to do. It is very well understood. Okay, there is not much new in it. Angular velocities also, I can either do this, but again, I won't go into this. There are no propagation formulas like this for parallel robots. Okay, so in case of a parallel robot, you have to go back to the basic definition of what is an angular velocity. You have to find out what is the rotation matrix. You have to do derivative of the rotation matrix into R transpose, R dot R transpose. Okay, so if anybody is not understanding this, you can either stop me and ask me questions and I will try to answer, or we can discuss this later. Okay. So as I said, little bit math is here. These notes have been given to everybody, so you can go back and just try to understand the basic concepts. So the basic, it's very simple. Omega of link 2 is omega of link 1 plus whatever is happening at the joint. Linear velocity is linear velocity at some point which I know into omega plus r. Okay, straightforward, very basic mechanics we are trying to do. How about potential energy? Potential energy in Lagrangian formulation we only consider gravity. So remember, this is a rigid robot with, there is no such thing as bending, there is no such thing as strain energy, there is no such thing as springs. Okay, those you have to add. If you want to include those you have to add. So whatever is natural to the Lagrangian formulation is only gravity, and gravity is potential energy is mgh. Okay, that is what we use in basic physics in mechanics. But this way, what it means here is the following. Okay, the robot need not be always from the ground. The robot could be hanging from the ceiling. It could be from the wall. Okay, so there the distance h is not obvious. Okay, gravity is always downwards. Okay, the distance h will be in some strange way. Okay, so hence, if you want to look at it in any possible combination, so then you have a gravity vector, you have the location of the CG of that link, okay, from that zero coordinate system, and then you take some sort of a dot product. And this minus sign comes because gravity is this way, which is opposite to the z axis. Okay, so don't get confused by this formula. It is nothing other than mgh, written in some way so that it can be generalized to any way the robot is taken. Okay. In potential energy, there is also always this reference potential energy. So it doesn't matter when you are doing dynamics or equations of motion. Does not matter what is the reference value from where it is taken, because later on we will be taking derivatives. So if there is a constant term in the potential energy, it doesn't matter, it will vanish. Okay. So what does the Lagrangian formulation say? It is very simple. You find the kinetic energy of each link, subtract the potential energy of that link, so Ke minus Pe, and then you sum over all the links. Okay, so if you have 20 links, or if you have 4 links, or if you have 6 links, you sum over each and every link. So at the end, this is the scalar, this is the scalar, these are numbers, so you are just subtracting and you are adding, and hence you will find a single quantity. And what is this quantity dependent on? It depends on what is the joint variable. So remember, so you can see that the angular velocity depends on theta dot if it is a rotary joint. The linear velocity will depend on what is the velocity of this. So there will be a translation at the joint, so some d dot will come. Okay, so dh parameter, theta and d, it was discussed. Okay, so eventually what will happen is this quantity here is a function of q, which is theta and d, and q dot, which is theta dot and d dot, and mass and inertia and length and all those things which are assumed to be constant. Okay, so we have a big function here which is given from this, and n is the number of link. So in a serial manipulator, if you have only rotary and prismatic joints, the number of q, which is called as the joint variable, is same as the number of degrees of freedom, it is same as the number of links, n. Okay, most times. I mean, why would you want to build a robot where there is no motor or there is no joint? Okay, so this is we know, and Lagrangian formulation, all it says is you do these partial derivatives. So dl by dqi, then dl by dqi dot, and then take the time derivative of all these things. And so for every I will get something here, d by dt, something here. And on the right hand side, you equate it to external forces and moments which are acting on at the joints. So these are the joint torques or joint sliding forces. So if you were to do this, I will get n equations because I have n of this I equals 1 through n, and then I will have equate all of these to it. So it's a very simple recipe. It's even simpler than making idli or some other recipe for any cooking. Okay, all you do is find kinetic energy, potential energy for each link, subtract them, sum them over all the links, and then take all these derivatives. Okay, and this you don't have to do it by hand. So if you are, nowadays there are computer programs which are available which will do derivatives for you, symbolic derivatives. How many of you know what is Maple or Maxima, or even MATLAB does it? Okay, so there are packages which will, if you say differentiate x squared, it will give you 2x. Okay, not like numbers. It will actually give you the expression. So all you need to do is this. Okay, and hence eventually I get the equation of motion. So it's very simple. Very, very straightforward and simple for a serial robot to find the equations of motion. There's nothing to it. And I can write lot of math, lot of symbols, lot of vectors, subscripts, superscripts, but basic idea is straightforward. Okay. Okay, so once I have done for each one of these links I equals 1 to n. Okay, this now comes the interesting part. I can organize all these equations in this form. Okay, so all serial robots equations of motion can be written in this standard form. Okay, that is a very nice property of equations of motion for a robot. So what do we have? I have something called as a mass matrix. It is an n by n matrix into q double dot. Q double dot is like theta double dot or d double dot, the second derivative of the joint rotation or joint translation. I also have one term which is this matrix into q dot. This is called as the centripetal and Coriolis term. Okay, so if you go back and remember in mechanics, you will have something called omega square r. Okay, or you will have something called 2 omega cross v. Okay, so these are terms which come from derivative, second derivative when you take omega, Coriolis term, acceleration. So all the Coriolis and centripetal terms are here. This g of q is called as a gravity term. So this is what is coming from the potential energy, and the right hand side is torque. Okay, so every single serial robot can always be written in this form. Okay, so there is no exception. Okay, so I have an n by n matrix, another n by n matrix, an n by 1 vector, and this. Okay. So any question? Okay. So now people have worked on this. They know that somebody found out that all equations of motion are always of this form. So then if you know all the equations of motion are of this form, then why would you want to take all those derivatives? Okay, it's a pain. Okay, but you have to do it by hand, you have to be careful, and you have to make sure that derivatives are not done properly. So instead of that, we can even just go back one more step. Okay, so if you look at the kinetic energy, people have shown that the kinetic energy is always in this form. So I found out the kinetic energy of each link, link 1, link 2, link 3, I added all of them up. So then you ask a computer, or you write a small program to collect or the terms in this form. So it is q dot transpose into mq into q dot. Okay, so you collect, so remove all the theta double dot terms or theta dot terms and write it in this form, the kinetic energy, and this mass matrix turns out to be the same as what is there here. Okay, so I don't have to go through all those steps. Directly from the kinetic energy, I can find out what is the mass matrix. Okay, and the kinetic energy is always greater than or equal to 0. So we know kinetic energies are never negative. Okay, that is very useful because this kinetic energy greater than 0 means this matrix is positive, definite, and invertible. So later on during simulation, we will need the inverse of this mass matrix. Otherwise, we can't do simulation. Okay, so this must be symmetric and positive, definite. They are the real. All those nice properties are there. Similarly, the this term, this matrix, can also be found out without doing all those derivatives. Okay, so it turns out that this is slightly tricky, but it is also, there's a lot of math behind it. That once I know what is the mass matrix, so it is like n by n matrix. Okay, ij components are there. So if you do this derivative dmij by du ek mjk by qj and so on, you will get this Coriolis term, Coriolis matrix. Okay. And gravity term is nothing but take the total kinetic potential energy and take the partial derivative. Okay, so without doing the ddt and so on and assembling it, directly from the kinetic energy and directly from the potential energy, I can find out the terms in the equations of motion. Okay, and this is true for all serial robots. It is not for 2 link or 5 link or 200, it could be 200 links also, doesn't matter. Okay. So in math, if you, those of you who have done any, looked at any advanced course in math, this is a very important part in what is called as differential geometry. Okay. So in differential geometry of curves and surfaces, you will get this Cij terms. These are called Christoffel symbols. Okay, so somehow geometry and math and dynamics, they are all related in some sense. Okay. Just very little, I don't want to go into too much detail because Professor Madhupad will do all these things tomorrow. If you are doing parallel robots or if you are doing mechanisms, okay, you can extend this Lagrangian formulation to derive equations of motion of those also. Okay, because it doesn't make sense that I have only one formulation for serial which does not work for parallel robots. Okay, then people will say, what is the use? Okay, it is too narrow and focused. So if you have a parallel robot or a mechanism, you get what are called as loop closure or constraint equations. So in a 4-bar mechanism, you go around the loop and you come back to the same place. Okay, so that is what is called as a loop closure equation or a constraint equation. So if you have constraint equations, so there are m of them, you can extend the Lagrangian by taking the old Lagrangian whichever you had earlier, and then you subtract this quantity lambda j into njq. So from the loop closure equations, you do some multiplied by what are called as Lagrange multipliers, subtract it, and then you get a new Lagrangian, and again you can take all those derivatives and find the equation of motion. Okay, so this is just a nice way of, because it is extendable. Those of you who are interested in Lagrange multipliers and what are the properties of these Lagrange multipliers and how we can derive the new Lagrangian, you can go back and see there are some very well-known standard textbooks. Okay. And once you have the equations of motion, again you can find out, do all these things, and then what you will get is the left hand side looks very similar, the right hand side, one part is very similar, but then you have these, one new matrix will come which is related to the constraint equations. And so some of these slides are taken from the NPTEL lecture, where I also discuss serial and parallel robots at the same time, because it's a unified way of looking at everything. So don't worry what is K and K star, they come from the loop closure constraint equations. Okay, so you can find out what this K and K star are from this, assemble them together and get this side, and then you get this. So you have to add one additional term for parallel robot. Okay. And I'm going to skip this for the moment. We can come back to it a little later. Okay. So basically, summary in serial robots is that I can find the equations of motion, I can extend it to what are these called as holonomic constraints and loop closure equations. Okay. what are the problems in Lagrangian formulation? We should know what are the limitations of any method. So one important thing is it does not contain friction or any other dissipative term, and that is because this Lagrange was this very famous mathematician. How many of you know who is Lagrange? So he is from the time of this Newton and Lagrange and Euler and so on. So those days they were working on how the planets move around the sun. Okay, all of this is coming from that orbital mechanics and planetary mechanics. So what is friction there? If the Earth is spinning around the sun and rotating, there is nothing to do with friction as such. So there were no way to include dissipative terms. Okay, but we need friction. No, in a robot, every joint, every motor has some friction in it. Otherwise the robot will move around forever. We give some voltage and it should keep on moving. That doesn't make sense. So how do we modify this good, very nice formulation to include friction? So this is one of the problems. You do it in a very ad hoc manner. Okay, you just add at the end some friction term. Okay. So there is nothing, it doesn't come directly from the formulation. So what is friction? So maybe you know that the friction is proportional to theta dot, like viscous friction. So you just add C1 into theta 1 dot in the first equation, which is related to theta 1. If you know some other form of friction, you want theta 1 dot square, you can add it yourself. So it is not coming directly from the equations or the Lagrangian formulation. Okay, so typical models of friction is you have some constant, which is Coulomb friction, and then there is something which is proportional to Q dot, which is like viscous friction. Okay, C Q dot plus C1 Q dot plus C2. That is what you will add in the first equation. Second equation, some other term. Okay, so you keep on just adding these friction terms. It also does not contain anything to do with flexibility, backlash, or any other dynamics which you have not modeled. Okay, it is a very basic system for conservative system where kinetic energy is there, potential energy is there, and nothing else. So if the robot is, for example, moving inside water, okay, how will you model the force which is felt by the robot when it is dragged? You can't do it. Okay, you have to add it manually in an ad hoc manner. Okay, or if there is a gearbox in your robot and the gearbox has backlash, in the sense, backlash means what? You rotate one way, it rotates, and when you go back, nothing happens for some small angle. Okay, so how will you model that effect? You can't. The normal Lagrangian formulation does not allow you to take into account all these things. You have to do it manually. Okay? So I am going to stop here about this formulation. Is there any question? Then we can go forward. We can go and look at some examples and simulation, which will be much faster.
So in which cases we have to take the viscous damping?
Yes. So if you, So if you want to include friction, viscous damping, Coulomb damping, any other kind of damping, you just have to add it to the right hand side. Okay. So is this clear? Very basic, but I thought I will just give you some basic idea which can be extended. There are lots of books, notes are there, you can go through them in detail. Okay, so let's go and see some examples. What exactly happens when you apply this formulation to a simple robot? So what is the simplest possible robot? This is what we do in class. Okay, because in a class I cannot draw a 6 degree of freedom robot. I cannot derive equation of motion. If I start in the morning, then it will take about 3-4 hours, and everybody will fall asleep. So the simplest possible robot is this 2 degree of freedom robot, which is that there is one link here, another link here. Each link, so for example, link 2 has mass m2. The location of the CG is at R2. The length is L2. And this is a planar example. I mean, the links are moving in a plane. So if the links are moving in a plane, then only the IZZ component is important. There is no need to worry about IXX, IXY and so on. Only the IZZ component is important. So I2 is IZZ2 of this link. So similarly for the first link you have M1, L1, R1 and I1. Okay. So let's try and derive the equation of motion for this simple 2 degree of freedom planar robot. So what do? So if you go back and see, so this link, so what is the angular velocity of this link? It will be related to theta 1 dot, right? You know, this link is rotating by some theta 1. What will be the angular velocity of this link? It will be some related to theta 1 dot and theta 2 dot. How about the linear velocity of this link? We can go back to our basic physics and see that the velocity vector will be perpendicular here. This velocity vector will be this velocity vector plus omega plus r. Okay, so this is the very basic, this is a good idea, we have this in mind, we know exactly what is happening. But let's apply the basic formulas. Okay, so the formula is very nice. So for the fixed link, nothing is moving. So the linear and angular velocities are both 0. Okay, so the first link, if you go back and see the formula, it was linear velocity of this plus theta 1 dot. So you get a velocity, angular velocity vector. The linear velocity is still 0 because it's the linear velocity of the origin. Okay, the origin is here. Origin is here of the links. Okay, in DH convention, the origin is always at the joint axis. It is not at the CG. So linear velocity is still 0. What about the linear velocity of the center of mass? It is 0 plus omega plus r, whatever I told you, and you will get this term. For I equal to 2, what happens? Angular velocity will become theta 1 dot plus theta 2 dot. Linear velocity is this, and linear velocity of the center of mass is this plus omega plus r. Okay, so it's very straightforward, it is automated. Okay, then kinetic energy. So kinetic energy, if you derive, it is half v1 square mv1 square plus half I omega square plus half I2 omega square plus half mv2 square. Okay, these are the 4 possible terms, and it turns out that you will get this. So what is the key thing here? It is theta 1 dot is there, theta 2 dot is there, but also C2 means cos theta 2 will appear. Okay, so why is cos theta 2 appearing? So let's go back to this. So if this theta 2 is, let's say this link is folded here, okay, then the linear velocity of the link will be much smaller than if it is folded completely outside. So the linear velocity of the center of mass changes with theta 2. Okay, that you can see here, and that comes out in this expression here. Potential energy, it is, let's go back and see this, sorry. So potential energy, so this is 0, this height which is sum into sine theta 1, and this height from here to here which is sine theta 1 plus theta 2. Okay, so you will get something which is in terms of sine, whereas the kinetic energy has cos. That is all I wanted to point out. So you will get some mgh plus mgh and 2g and so on. So once we find the kinetic and potential energy, we form the Lagrangian. This is very straightforward. And then you to take all this derivative. So this is very mechanical. So if I take with respect to theta 1, I will get this, theta 2, theta 1 dot, theta 2 dot, I will get this, and then d by dt you will get this, and then finally assemble. Okay, and how do I assemble? I assemble keeping in mind that finally I want to write m into theta double dot plus c plus g. Okay, so if you were to write this, I will get theta 1 double dot into something, theta 2 double dot into something. So these are the Coriolis terms. So you will get something like theta 2 dot square. You will get something like theta 1 dot into theta 2 dot. Okay, similarly tau 2. So this is the equation of motion. So it's very straightforward and simple. You can derive it in the class and you can show it. Okay. And you can organize it like this way. and you can show that this is the mass matrix, this is the centripetal term, this is the gravity term, and so on. No friction is there because the friction was not modeled. Okay? So what do we do with this equation? As I said, there are two problems which we want to solve. We want to find out what is the given torque, in this case the two motor torques tau 1 and tau 2, how the robot moves. Okay? Or secondly, if I give a path, find out how much torque is required to make it move on that path. Okay? So that is called inverse dynamics and simulation. So let's try that. So inverse dynamics, rephrase the problem. Given dh and inertial parameters, trajectory as a function of time, find joint torques. Direct problems, given kinematic and inertial parameters, obtain q of t from this. Okay, so this is, as I repeated right in the beginning, this is for finding out what size motors to use, and this is to show actually how it moves. Okay. Inverse dynamics is very simple. Why? Because you are given q, q double dot, q dot, everything, the right hand side is just given. Okay, as I said, the trajectory is given. I want to move first joint constant velocity, second joint in some particular form, and hence I know exactly what is q as a function of time is, theta as a function of time is. So all you do is just substitute and put it on the right hand side. So you just quickly get the torque. Okay, and as I said, I can do this very, very efficiently. You can do it in ON steps, and you can prove that inverse dynamics, the Newton-Euler formulation, there is a nice proof which says that it is always in ON steps. It's a linear complexity problem for serial robot. Okay, so let's take an example. So this is an example, some numbers. Now you have to use some numbers. So the mass of each length is 1 meter, mass is 12 kg. This 12 comes from the fact that there was actually a robot which was built. So the first link normally of a robot is, is quite heavy and inertia is quite big and so on. So if I want to trace the tip of this robot on a circle, okay, so let's say I choose x is some a plus r cos phi, y some r is this and so on, and I want to make this robot do this circle constantly in some time. You have to choose some numbers right now. Okay, so I want to know now for this particular trajectory what is tau 1 and tau 2. Okay, so I can just substitute on the right hand side and then we get this. So here is the plot. So theta 1 as a function of time is this, theta 2 as a function of time is this, theta 1 dot as a function of time is this. These are given to you, theta 1 dot is given, and then this is what torque which you will get. So if my robot were, the job of the robot was to trace this circle with this time, what should be the motor torque? We can say that it should be at least this value. Okay, the motor should be able to deliver at least this much, this many Newton meters. Okay. So this is very straightforward. Inverse dynamics, nobody worries about it. You just substitute. Okay. And how about simulation? It's a slightly more harder problem because now we need to solve equations of motion. Because in simulation, what happens? This left hand side is given to you, torque. So you are saying that I am applying so many Newton meter torque at first joint, so many Newton meter torque at the second joint. I want you to tell me what the robot does. I will show you some of the videos later on. It will not work if I click right now. Okay. So I have to solve these equations of motion. So how do you do? So basically it's a set of n second order coupled ODEs. Okay, these are nonlinear. You know, you saw that there was theta 2 at one of the thing. There was sine theta 2, there was cos theta 2. It is not a constant equation. Okay, the coefficients are not constant. Coefficients are functions of theta.